Now we're just going to do some review. So first, what is the equation of the tangent line of the circle at x squared plus y squared equals 25 at the point 3, 4? Pause the video, do that, unpause when you're ready to check. So just like our notes from last night, this is an example of where you could have done implicit or explicit differentiation, but implicit differentiation is going to be much easier to do this problem. So our answer should be y minus 4 equals negative 3/4 times the quantity x minus 3. How do we get that? I did implicit differentiation, so the derivative of x squared is 2x, the derivative of y squared is 2y dy dx, derivative of 25 is 0. Solve for dy dx, I get negative x over y, plug in the point 3/4, so I get negative 3/4, and then I know the point 3, 4, so y minus 4 equals negative 3/4 times the quantity x minus 3. Hopefully that's pretty straightforward. Next, find the slope at x equals 1 of this function. Pause the video, unpause when you're ready to check. Here we should end up with 7 root 5 over 10. How do we get that? Okay, back to the top. So we're doing the quotient rule, the product rule, and the chain rule. Again, look at this lovely color coding on my part. I know, it's good, right? So I did bottom times the derivative of the top. In the derivative of the top, I have to do the product rule and the chain rule. So for product rule, I did the derivative of the first times the second plus the first times the derivative of the second, which is the chain rule. So I did the derivative of the outside and then times the derivative of the inside. And then continuing on with quotient rule, minus the top times the derivative of the bottom over the bottom squared. Now at this point, because all we were trying to do was find the slope at x equals 1, I just plugged in 1. I didn't try to simplify at all. Plug in 1, now I combine like terms, simplify, simplify, and I get 7 root 5 over 10. I do want to point out, so I didn't specify on this, and hopefully you did this problem by hand, but make sure you know how to do a problem like this on your calculator as well, because remember that can save you a ton of time, right? That from the very beginning, just put this into y1, and then y2, do n derive of y1, and then look on your table when x is 1, and that'll give you your answer. Now the difference is this is an exact value, the calculator will not give you an exact value, so pay attention on the test if I ask you for an exact value or not. But that's something I want to point out, that you could find this on the calculator very easily. And make sure you know how to do that. Next one, find the equation of the tangent lines to the point 4, negative 3, not on this function. So we want to find the equation of the tangent lines to this function that go through the point 4, negative 3. And remember, 4, negative 3 is not on the function. Pause the video, unpause when you're ready to check. Okay, so here we should end up with 2 lines. One is y plus 3 equals 20 times the quantity x minus 4. And the other is y plus 3 equals 0 times the quantity x minus 4, which is actually just the line y equals negative 3. So both lines go through the points 4, negative 3. Now, how do we come up with that? Well, remember, this is where we've done these problems before, but it's been a while probably. So this is where we have to really think about, what does the derivative represent? The derivative represents the slope of every tangent line. So I find the derivative of my function, 2x plus 2. Okay, that is the slope of all of the tangent lines. I want the tangent lines to go through the point 4, negative 3, so I just write the equation of this line. So y plus 3 equals slope, which is 2x plus 2, times the quantity x minus 4. So this is point slope form of a line, but for the slope, I'm plugging in a function that represents the slope. So now I brought everything over to one side and simplified a little bit, so I get y equals 2x squared minus 6x minus 11. Alright, that's great, that's a quadratic function, but how do I use that? So normally our instinct would be to find the zeros of this function, but that's not what we need to do here. We need to think about, okay, how does this function relate to what I already have? Well, this function represents the equation of the tangent line. So in order for this to be a tangent line of this function, that means that it has to touch or share a point, or in this case points, with this function. So I have a system of equations. So I can set the function, since this equals y and this equals y, I can substitute the function in for y, because they have to intersect at the point of tangency. So that's my relationship, that they have the same slope, they have to intersect at the point of tangency. So that's the substitution. Now I bring everything over to one side. Now I find the zeros, and I get x equals 9 and x equals -1. So then I go back to my derivative, and I just plug in 9 and I plug in -1, because remember, that's what this x represents, is the slope. I don't need a point, I need the actual slope. I want a value for the slope. I don't need a point at this time. So x equals 9, I plug that in for x into my slope, I get 20. X equals -1, I plug that in, I get 0. So then I can write, I go back up to my original slope, or my original line equation, but I plug those numbers in. So those are the x values on this function where the tangent lines hit that go through the point for -3. Alright, next, what makes a function differentiable at a point C? Pause the video, answer that, unpause when you're ready to check. So this comes down to our alternative form of the derivative. So remember, if the limit as x goes to c from the left of the alternative form equals the limit as x goes to c from the right of the alternative form, then the function is differentiable at that point c. Next one, we love these types of problems because we've seen this a lot and we love it. Find k such that y equals -2x minus 5 is tangent to f of x equals kx squared plus 1. So this is similar to, but not the same, as the problem we did 2 examples ago, where we're trying to find some value of k that makes this the tangent line to this function. So pause the video, do that, unpause when you're ready to confirm how correct you are. Alright, so here we should end up with k equals 1/6. Okay, how do we do that? Well, a couple things we need to talk about. So, if this is the tangent line, the slope of the tangent line is -2, so I know the derivative of the function needs to equal -2. So I find the derivative of the function, which I just do my power rule, so 2kx. Remember, k is a constant here, so we don't do the product rule with this. So I get 2kx equals -2, because it has to equal the slope of the tangent line that I'm trying to find, right? Alright, so then I just rearrange this and isolate k. So k equals -1 over x. What is my other relationship? This is what I was talking about, that it's the same as 2 examples ago, where if this is the tangent line and this is the function, the tangent line has to intersect the function at the point of tangency. So they share a point. So the tangent line and f of x share a point, so therefore I can do a substitution to find where that point is. So I can say -2x minus 5 equals kx squared plus 1. So I'm substituting, because normally these both equal y. So then for the k, I substitute in -1 over x, simplify, solve for x, and I get x equals -6. So then I take that -6 and I plug it back in here, and I get k is 1/6. So when we're doing these problems, we're really just solving a fancy system of equations using derivatives. It's one way to think about it. Alright, so it's really important that we know when and how to use the product, the power, the quotient, and the chain rule. It's also very important that we understand what a derivative represents, that it is the slope of a tangent line. Another way to say that is it is the instantaneous rate of change of a function. It's very important that we recognize when to use implicit differentiation as well. So that's the new thing that we've learned since our last quiz. But that's a crucial part of derivatives.